17.10 has to do with a whole new type of reaction that we haven't talked about yet, and that is complexation reactions. This is where a transition metal cation acts as a Lewis acid. Remember, a Lewis acid is an electron pair acceptor, and metal cations will readily accept electron pairs to form new coordinate covalent bonds to other species in solution. Okay, and we call the new small molecules or ions that act as Lewis bases, we call them ligands, and we will call the Lewis adduct, or in other words, the product of these reactions, if they are charged, they will be a complex ion, or if they aren't, we could call them a coordination complex. Or just a coordination compound. And so sometimes it's called complexation chemistry or formation reactions. Oh boy, there's a lot of names for this. So formation reactions is maybe the most general term that I'll use for the reaction as a whole, and then I'll probably jump between these two pretty fluidly, complex ion or a coordination complex or coordination compound. And ligand, again, are the Lewis bases, which will donate electrons to the metal cation to form new bonds. Okay, so usually these are equilibrium reactions with a product-favored equilibrium constant. So let's consider the reaction of cobalt, what is this, cobalt 2 plus, and this will be aqueous, plus ammonia, and there will be 6 ammonia. There will be 6 ammonia molecules that will form coordinate covalent bonds with that cobalt. And in the end, you get a complex ion that looks like this. And so the equilibrium constant K here, we'll call it Kf. It is a formation constant. Just like for acids and bases, we gave a special name to its equilibrium constant, an acid dissociation constant, or a base dissociation constant, or an acid ionization constant. We just call it a Ka or a Kb. Well, here we have a formation constant, or a Kf. And the Kf in this case is going to equal the concentration of the complex ion, which I should have written its phase, it's aqueous, in the numerator, and then in the denominator we'll have the metal cation itself, and we'll have the ammonia. And that'll be raised to the 6th power. And so these complexation equilibria will often have high powers in their equilibrium expressions, and that makes for some unexpected results sometimes and some fun math. And in this case, that is equal to 5.0 times 10 to the 31st power. Not negative 31, that's a positive 31. And so this reaction is highly product favored. There's going to be a lot of the cobalt hexaamine complex ion, and not very much of the metal cation cobalt or the ammonia around at equilibrium. These can get a little bit tricky at certain concentration values, but anyway, it's generally a highly product favored reaction. 10 to the 31st is really, it's a bigger number than whatever you're thinking of. And if you're thinking that it ought to be a bigger number than you're thinking of, and you adjust your thinking appropriately, it's still bigger than that. It's a huge number. So let's look at a table 17.3, which gives some examples of some complex ions. And you know, if they just give you the complex ion, you need to be able to figure out what is going to be the reaction that forms that complex ion, and how I can create an appropriate equilibrium expression. So let's pick the bottom one, the iron hexacyanide, and let's try to work backward to create a chemical equation and an equilibrium expression. So our product is FeCN6 3-. This is going to be an equilibrium. And what are the components that make up this iron hexacyanate? Well, we're going to have 6 Cn minuses, and we'll have an Fe. And what's the charge on the iron? Well, when it's paired with 6 cyanides, we get a total charge of 3-. And so that iron is in the 3+ state. That way our charges balance. Let's get rid of this table now. I don't think we need it anymore. And so the Kf is going to equal concentration of the complex ion times the concentration of the iron 3 ion and the concentration of cyanide raised to the 6th power. So just by seeing that product, you should be able to sort of reconstruct everything you might need to do some math with equilibrium chemistry. And whenever we have a Kf, our ultimate goal should be to like find the equilibrium concentrations given a certain set of starting conditions. But these problems are a lot different than what we've seen before. And to illustrate that, let's do a practice problem. And we'll try to solve it kind of naively the way we have been doing. And I'll just tell you now, that's the wrong way. We're going to run into a big problem. And I think it's best if we go through that process and hit that problem and see exactly why it is a problem. So we're going to go back to that cobalt reaction. Cobalt plus, what is it, 6-amine plus 6NH3 in equilibrium with the complex. So let's do an ice table. Okay, and let's assume we start with a cobalt concentration of 0.020 molar. And we start with an ammonia complex of 0.100 molar. And we've got none of our product. And remember, Kf is going to equal our cobalt, NH3 6 2+ concentration over our cobalt 2+ concentration times our NH3 concentration raised to the 6th power, and that is equal to 5.0 times 10 to the 31st. Okay, so that will become important. So what we'll have is like a minus x and minus 6x and plus x, and so we end up with x. 0.1 minus 6x, 0.02 minus x. And so we'll get, maybe I'll do it down here, 5 times 10 to the positive 31st is equal to x over 0.02 minus x times 0.1 minus 6x, and that is raised to the 6th power. Now ordinarily at this point we say x is probably a small value, so I can ignore it here, and that would make everything really simple and easy to solve. Now if we do that, then this 5 times 10 to the 31st, we'd multiply it by 0.02, so I guess that becomes something like 1 times 10 to the 29th. And then we'd multiply it by 0.16 times, and so we're at 1 times 10 to the 23rd. X is equal to 1 times 10 to the 23rd. That is an absurd conclusion. That would say that we have a molar concentration of 10 to the 23rd. Obviously, X here is not going to be small. We have a product-favored reaction, so the amount of product that we form is going to be a large amount. So we're going to have to solve this without making any sort of assumptions. And now I've got x to the 6th here, x to the 1st power there. So this is going to ultimately be a polynomial with x to the 7th power. It will be truly tedious to FOIL this out when it's raised to the 6th power and to get it all in polynomial form. And even when we did, we have no quadratic formula for equations with x raised to the 7th power. So we're looking to be out of luck. But you might say, hey, I've got tools to make approximations. I could use my graphing calculator to set this side equal to that side. Or I could use Wolfram alpha. And so you proceed onward in your naive hope that this can yet be solved. And I actually don't have Wolfram alpha up quite yet. Okay, now it's ready. So we'll go to Wolfram alpha and we'll say 5 times 10 to the 31st is going to equal x divided by, we have 0.02 minus x, and we have 0.1 minus 6x, and that is raised to the 6th power. So there it is. We'll hit enter and we'll let the computer do all our work for us. We can sort of double check that everything was input correctly, and I think it looks fine. And we come down here and we get a solution that x is equal to 0.02. Actually, that's not going to be a good solution for a couple of reasons. Let me make sure I put this in correctly. Oh, I didn't. No, yes I did. 0.1 minus 6x raised to the 6, 0.02 minus x. Okay, well, Wolfram alpha has failed in a couple of ways. I think one of these complex solutions is actually supposed to be the right answer, and it's just got such a small imaginary component. But anyway, let's just kind of walk through these. Well, if x is equal to 0.02, then 0.02 minus x, that's going to equal 0. And I can't divide by 0. Furthermore, 0.1 minus 6 times 0.02 is going to give me a negative concentration for ammonia, so that's no good. We can come back to Wolfram, and like I said, let's look at these two values here. 0.0166666. If I take that and I multiply it by 6, so let's do this. Sorry, got too many things going on. Okay. So if I take 0.016666666666667 times 6, and that's 0.1. And so if we come back here to 0.1 minus 6 times x, that's equal to 0.1. And you might say, oh, there's a 2 out there. Well, that's just because I didn't carry the 6's all the way. And Wolfram didn't either. But you can see what's clearly happening here. That's like 2/3, right? That's a repeating decimal. And again, it's just not going to work. It's going to give us a 0. If we divide by 0 right here, well, that's a problem. And then there's one final solution. We'll come back here to Wolfram. This 0.0167, well, that's greater than 0.0166, and so if I take my 0.1 minus 6 times that, again, it'll give me a negative value. None of these solutions seem to work. And in principle, this approach should work. There's nothing wrong with it mathematically, but Wolfram Alpha or using your graphing calculator, those are tools that find approximate solutions. And the reality is they're not carrying enough significant figures forward into the answer to work. Like the approximation that they make is too coarse, it's too rough, and you're not going to get the right answer. So what's a chemist to do? Well, I'm just going to erase all of this. We'll end up redrawing a little bit of it in a second. We'll leave that. Okay. We can think of our chemical equilibrium system like a valley that has a middle point. We'll call this the equilibrium point. And if I have a ball, we'll make it a tennis ball, it will roll down and it will eventually settle here into that equilibrium position. This is a sort of a visual representation of the reaction starting with only cobalt and ammonia and 0 amount of the complex, and rolling toward that equilibrium position means it's reacting forward to produce the appropriate amount of cobalt amine complex to satisfy the equilibrium expression. Well, if I have the ball starting on this side instead, in other words, if I, with mathematical consistency, sort of force the reaction to go all the way toward products, as far as it can go, so that I have a lot of my complex and then 0 amount of my limiting reactant, and then I allow the ball to roll back this way, it's going to end up in the same position. I think I can explain this a little bit better with numbers, but I just want to make the analogy kind of complete here with the balls. It doesn't matter where the ball starts. It could start here, it could start here, it could start there or there. As long as it's rolling on the same hill, then it's going to end up at that same position down there at the equilibrium position. And what we have here is a very uneven hill, like looks like this. And you know, if we start on the reactant side, it's going to roll pretty much all the way to the right in order to reach equilibrium. If we start it on the product side, it just has to move a tiny bit before it reaches that equilibrium position. And our problem was that x, our value for our change, was too big. So this is a big x, or a big change in our ICE table. This path here has a small x. And that just might make our math a little bit simpler. So what we'll do is sort of mathematically push the system as far as we can toward products and allow it to react backward, regenerating reactants in order to reach the equilibrium point. And if that analogy was helpful for you, great. And if not, then perhaps it'll make more sense with our actual numbers here. So remember, we had 0.020 and 0.100 and 0. Now this time, instead of an ICE table, I'm going to do a BCA table. Before, these are the before amounts, the change, and the after. So what is the amount of change? Well, I'm going to make this reaction go forward as much as it possibly can. One of these is going to be the limiting reactant, and so I'll drive the reaction forward until the limiting reactant reaches 0. Well, let's just quickly figure out which one is the limiting reactant. I need 6 times as much ammonia relative to the amount of cobalt. Well, 6 times 0.02 is 0.12, but I only have 0.10. That makes ammonia my limiting reactant. So we will subtract 0.100, and we'll end up with no ammonia afterward. Well, how much cobalt do we make? That would be 0.1 divided by 6. Let's not take any chances here. Let's figure what that is. 0.1 divided by 6. Okay, that's 0.0166, and again, this is that same repeating decimal answer that Wolfram alpha gave us. Only instead of being the change in an ICE table, this time it's the change in a BCA table, and that's going to be significant. So we'll say we have plus 0.016667, and we'll just carry a few extra digits just for fun, and this will be negative 0.016667, and so we end up with 0.016667. Let's just do 5 sig figs, that'll be plenty. And then again, let's not try to do too much math in our head. 0.02 minus 0.016667. We'll just carry those 5 sig figs. And we end up with 0.003333. 0.03333. Okay, so this is the amounts that we have after we've pushed the reaction as far toward products as we can. These numbers are chemically consistent with these numbers. They represent a ball that's on the same slope, it's on the same hill, but it's starting at a different position. And what we'll do is we'll take these numbers now and we'll put them in an ICE table. And I normally like to do like a second ICE table to the side, but I just don't have enough board space, so I'm going to have to erase some things here. So we'll erase all of this. And these will now become our initial concentrations. So we have 0.03333, we have 0, and we have 0.016667. Okay, now we can erase from our BCA table. The after line of the BCA table becomes the initial line of the ICE table. So now it's an ICE table, ICE. And what will the change be? Well, since I have 0 ammonia, I know that I'm going to have to go in reverse. I'll have a negative x here, plus 6x there, and a plus x there. And so my equilibrium amounts are 0.016667 minus x, 6x, 0.03333 plus x. And now we can put those into my equilibrium expression. I'll do it down here again. I have more room down here. 5.0 times 10 to the 31st is equal to 0.01667 minus x over 0.3333 plus x times 6x. Now, is this any better than what we had before? The answer is yes, because now we know that x is small. X is the amount that we go backward to regenerate some reactant. And we know that we have only a teeny tiny amount of reactant because that Kf is so very large. And so if X is small, then I can assume that's pretty much close to 0. And I can assume that is pretty much close to 0. Oops, and that 6x should be raised to the 6th power. Goodness, I forget that altogether too often. Don't forget that. And now, even though I've got that x to the 6th, that's the only x in the whole equation. We can rearrange this. We'll say that 5.0 times 10 to the 31st is equal to 0.016667 over 0.03333 times 6 to the 6th times x to the 6th. And now, hopefully it's pretty clear that we can solve for x. X is going to equal the 6th root of 0.016667 divided by 0.03333 times 6 to the 6th times 5.0 times 10 to the 31st. We'll raise that to the power of 1/6 to take a 6th root. I'll erase this one just so we have room somewhere to write our answer. So we have 0.016667 divided by 0.03333 divided by 6 to the 6th power divided by 5.0 e positive 31. And all of that is going to be raised to the power of 1 divided by 6. And I get 7.74. X is equal to 7.74 times 10 to the negative 7th. Okay, x is 7.74 times 10 to the negative 7th. Is that indeed smaller than these two numbers? Yes, it is much smaller, and so our assumptions are good. And now we can turn these into concentrations. The concentration here is just going to be 0.016667 because the minus this tiny number doesn't affect it. The concentration here will still be just the 0.03333 because the plus the tiny number doesn't make any difference. And then this 6x, what is 6 times that number? Let's figure that out real quick. That's going to be 4.6. We only get 2 sig figs really. So 4.6 times 10 to the negative 6th is the concentration. 4.6 times 10 to the negative 6 is the concentration of the ammonia. I think these problems are not actually that difficult, but they're really kind of weird, and they're different enough that they throw students off often. So we're going to do a quiz today where we do 2 more of these problems so that you get plenty of practice. And that ends chapter 17.